Hello, everybody. Thank you very much for being here virtually and for tuning into this video. I'm pretty sorry for everybody at the graph signal processing workshop that you have to deal with a pre-recorded YouTube video, but unfortunately, due to some visa issues, I couldn't make it there in person. Uh, but yeah, I still need to thank the organizers of the workshop very much for having me there even in this kind of boring virtual format. And I'd like to thank every one of you for I'd like to thank every one of you in advance for your attention in the following 15 to 20 minutes. So yeah, as I mentioned before, my name is Gary Skanderi. I'm a postdoc at Bocconi University in Milan in the Machine Learning and Statistical Physics group. And today I'll be presenting this work, which is called Graph-Level Representation Learning with Joint-Embedding Predictive Architectures, which is work that I've done with some of my ex-colleagues at Michigan State University when I was visiting there, and other people at the University of Verona. So without further ado, let's just get started. I'll essentially here talk about graph self-supervised learning, as you can imagine by the title, where I'll first introduce this notion. Then I'll talk about Graph-JEPA, which is the model architecture that we propose in our transactions on machine learning research paper. And then I'll just wrap things up with a few directions for future work and ideas for extension of this architecture to some applications. So yeah. Well, as I'm pretty sure you've heard throughout the workshop, graph data is in fact ubiquitous in the real world. We see it, in social networks. We see it in molecule representations. We see it in motion capture, where one might have a spatiotemporal graph. So there's a lot of different data types. And, one common task that is pretty often necessary in these, with these data types is this idea of like solving a graph level task where essentially you have a graph and you want to translate this graph into some sort of representation that can uniquely, embed your information or the signal in the graph into a vector. So just a little bit more formally, you have your triple here. So you have a node set, an edge set, and a signal, which we usually denote by X. And you also have a structure that denotes the relationship, right, between the nodes, so effectively it encodes the graph, which is the adjacency matrix, and you want to translate all of this into a vector, right? So you want to have a fixed vector representation of the graph. Now, the reason you want to do that is, of course, because this vector representation can then later be used throughout a different multitude of models, but commonly now we use neural nets. So then you can use this representation to solve a task on the graph, whether that is to classify it. So, for example, you want to, maybe express what molecule type you're dealing with, or whether that be you want to regress a particular value that has to deal with the graph signal and structure, right? So as I mentioned before, in this talk, we're going to talk about self-supervised learning. So the idea is that we want to learn these features, so that this unique vector representation, in such a way that it does not require direct labels, right? So in self-supervised learning, usually you have a data set which is not labeled, and then you want to train a neural network to solve a task, which is essentially a proxy for learning these new features. And then you hope that once you learn these features, you can then transfer them in a downstream task, right? So this pipeline has seen a lot of success. Most foundation models nowadays are trained in this fashion. And, it's still a pretty big what if in the graph realm, because usually with graphs, we don't see a lot of this like pre-trained fine-tuned paradigms. And the big reason for that is because we don't know whether this notion of like universality of the features holds in this context. But that being said, usually self-supervised learning is done in two ways. And there's a third way, which is the one that we also propose in this paper, which has gained a lot of attention in the past 2 years. So the first way is usually called the joint-embedding architecture, commonly known as contrastive learning, or if I should say in a better way, contrastive learning is a specific instantiation of this self-supervision type. So here you have two signals, X and Y, coming from your data. You learn a representation of those signals, and then you compare them to each other via an energy function. That's what you usually call it, which is a distance, right? So if you want these pairs to sit closer together, so they need to have low energy and otherwise need to have high energy. The other way, which is very commonly used, especially, for example, in LLMs, is the generative architecture. So here you have a signal which you encode, and then you need to learn a decoder, which is essentially your generative model, such that from the representation you can produce a signal in data space. And then what you do is you compare this generation with the actual ground truth signal, right? So joint-embedding predictive architectures, which are a proposal originally of Jan LeCun, they essentially bridge these previous two methods. So you have, again, a signal X and a signal Y coming from your data, but you now learn a representation for both, just like you do in the joint embedding architecture. But instead of directly comparing these embeddings, you actually learn to predict one from the other. So it's as if you're actually trying to generate, right? So you're trying to learn a generative architecture in the latent space. And this is the framework we're going to be focusing on in this presentation. So without further ado, let me get started on Graph-JEPA, which is this first, let's say, modern JEPA framework for graph-level self-supervised learning. So Graph-JEPA is conceptually very simple. The idea is that you start with an input graph, which is divided into different subgraphs. And then each one of these subgraphs is fed through a neural network encoder, which is usually a GNN. And then you produce a fixed vector representation for each subgraph. Then you pick, very similarly to how you would do in masked modeling, you pick a context, and then you also pick a target. Actually, a bit more specifically, in our paper, we actually treat the case where there's multiple targets given the same context, but for the sake of illustration, I'm just going to keep a one-to-one correspondence here. So then once you pick a context and a target, the goal of your model is to predict the target representation given the context, right? So this is the whole game that you're trying to play with your model. Now, I will describe each of these steps a bit more in detail, and I'll be focusing mostly on the prediction part because that's actually where the quote-unquote magic happens. So that's the most peculiar part of the architecture. So for the partitioning, actually the partitioning is pretty straightforward. We just use a graph partitioning algorithm, which is called METIS here, very well known. And the idea of the partitioning is that you want to specify P subgraphs. So then your partition is a collection of these P subgraphs such that there are no nodes intersecting, right? So the nodes in each subgraph are uniquely define the subgraph, excuse me. And they all have a cardinality, ideally, that is essentially the number of nodes divided by, oh, sorry, there's an error here that's supposed to be a P, not a K. And of course, you want to make the partition such that the union of all partitions gives you your graph. Now, a little detail here is that if you can see the diagram, actually there is an intersection between the nodes in those subgraphs, and that is by design, because what happens is that if you uniquely specify the subgraphs, what happens is that then when you learn the features in these subgraphs via the GNN, the features essentially become too unique, right? So the idea of learning via message passing, very similarly to convolution, is that you want to have this idea of local aggregation, which we don't want to use. So to do that, we actually do a one-hop neighborhood extension here, where each subgraph, so the nodes in each subgraph, they are connected again to the nodes that were their one-hop neighbors in the original graph. So in this way, we have, essentially in simple words, we have some overlap between the different subgraphs, right? So as I mentioned before, then these are fed into this GNN encoder. So in our case, this is a graph isomorphism network with edge features potentially. And then you pool these representations to create a unique vector for each subgraph. So in this case, I'm just picking two of these subgraphs. One of them is the orange one, the other one is the green one. And once I have these vectors, what I do later is I just feed them into an encoder, which in this case is a graph transformer. So in this case, essentially you have that you process the information in each of these vectors in relation to the others. So again, in this diagram, I only have two, so it's essentially just a multilayer perceptron acting on each subgraph representation. But remember that potentially you can have multiple target subgraphs. So in that case, you learn via similarities on those target subgraphs. Okay, so now I hope this part is all clear. Now we get into the more intricate or like the more design-specific choices. So now the goal, again, I mentioned, is to predict the target encoder representation via the context. Now, if you just do this, simply, you can, of course, implement that. But the idea is that here you can make some assumptions about the type of representations you want to learn. And so for us, this kind of ansatz that we try to have is that graph data has inherently a hierarchical structure when it comes to having a single descriptor at the graph level, right? So if you want to describe the whole network using a single vector, then interactions within the network will usually follow a hierarchical structure. And as I'm pretty sure you might have heard or also worked yourself in geometrically inspired methods, hyperbolic space is a very common choice where one can represent such hierarchical relationships, right? So that is exactly the approach we take in this paper. But we do propose a very simple trick and workaround to avoid essentially kind of the problematics associated with working with hyperbolic neural networks. So the first thing we do is, of course, we'd like to have a prediction task, which is in a certain sense conditioned on some positional information. So we can make this task a little bit less ill-posed. To do that, we use a simple random walk positional embedding on the nodes of each subgraph, which is depicted below the red PE sign there. And then to have the random walk positional encoding of the subgraph, we simply take an element-wise maximum of the node's positional encoding. So in a certain sense, the simple words to describe this is that each subgraph is positionally described by the most central nodes in terms of random walk of length k. So once we have that, we actually feed that to the context representation. And then the goal is to use a very simple predictor. So as you can see, it's just a two-layer network in our case to predict the target. Now, the more interesting part is that we actually predict this target not in the embedding space, but we average the descriptor to create the hyperbolic angle. So we use actually the features of the target representation as a high-level descriptor of the hyperbolic angle. So denoted here by alpha. And then we use that angle to produce the coordinates in the unit hyperbola of the target representation. So now the prediction game is essentially that the context encoder needs to predict where in the hyperbola the target representation should belong, right? And in this way, what you have, so visually this process will look like this, is that you have this very simple game where you're just trying to guess in a hierarchical essentially submanifold where your target should be located. And this implicitly encodes this notion of hierarchy in our case. Now, of course, one here might wonder and be like, okay, what is the choice of D, right? Because this distance function in this case becomes pretty important. So in my diagram here, I've depicted a straight line distance, which obviously for points lying in a hyperbola is a bit, ill-posed, because the idea is that this hyperbola, the unit hyperbola, you can view it as a geodesic or essentially just a part of a hyperboloid. And in this hyperboloid, of course, you want to stay within the manifold. So ideally, one here would use actually the hyperbolic distance of the hyperboloid, which is relatively straightforward to compute for points in the unit hyperbola. It's just the inverse hyperbolic cosine of the negative Minkowskian metric applied to the representations. The issue is that very often computing these calculations with the inverse hyperbolic cosine can be very numerically unstable, and that is because in our architecture we don't have hyperbolic neural nets. So far up to this point, the embedding space is no way constrained, has never been constrained actually to have or respect any sort of hyperbolic structure. So, perhaps you can have computations where, for example, suppose that this inner product here can get close or very distant from -1 or very close to 1. In that case, you can essentially start to get in the very edges of the manifold, and that is a bit problematic numerically. So what we do to bypass this is that instead of using actually the hyperbolic cosine, we say, okay, in the unit hyperbola, essentially for reasonable distances, you can approximate this if you have like essentially a smooth L1 distance. So unless very extreme cases where you're in one part of the hyperbola and you're trying to predict something that's on the other part, this approximation is, let's just say, very cheap. It's obviously not correct because you're going to deviate a bit for the manifold, but it does approximately hold, right? And I will show later that in practice, this seems to actually work very well and also avoid any sort of numerical instabilities, even in high dimensions. So yeah, the final part of the architecture is the training procedure. So here, a very important thing to note is that the training is done by actually applying a stop gradient operation on the target encoder and having an exponential moving average at the update of the weights instead of gradient descent. So this is a very common procedure, even for example, in BYOL or other well-known self-supervised learning architectures. And the reason you want to do that is because if you just train the full network via gradient descent, you can consider a very simple case where your predictor is linear. So you have W here, the weights of the predictor, and then you have X and Y, the context and target signals respectively. If you want to solve this problem via ordinary least squares, what you end up with is that you need to essentially solve for an orthogonal projection, which is very well known. And of course, if you want to solve for an orthogonal projection, the easiest vector you can choose to do that is the zero vector, which is orthogonal to itself. So what that means is that your representations will collapse, right? So to train these architectures, a big takeaway is that you need a lot of these training tricks. So to wrap things up very quickly, I'll just present the results because, of course, I'm sure that you all know that in machine learning, we always have optimal results and, everything is in boldface. So here, I don't want to spend too much time on this table. We essentially test Graph-JEPA against the contrastive and generative approaches in graph self-supervised learning, and we find that the architecture is very competitive in a lot of different tasks. But a very interesting result, which we found, is that if you actually train the model on graphs and then you use it to essentially infer whether two graphs are isomorphic, as in the picture here, Graph-JEPA actually performs much better than a lot of GCN architectures, which are well known to be limited in this aspect. And actually almost matches the perfect performance of graph MLP mixer, which is trained in a supervised fashion. So just by doing this whole unsupervised or self-supervised, better said, procedure, we can almost match the perfect performance of a supervised architecture such as graph MLP mixer. And then finally, I just want to show the impact of this kind of coarse hyperbolic task that we designed here in the embeddings. So here you can see on the left, if you would just predict the embeddings normally as you usually do using the Euclidean distance, and then you can see how hyperbolic the embeddings are shaped if you use our task. And we also find that our approximation works much better actually than the Euclidean distance, both in low dimensions, depicted here by LD, and also in high dimensions. So it's both numerically stable and it induces this hyperbolicity notion, right? And as a final thing, the method also turns out to be pretty computationally efficient, which is a good sign for scaling, right? So it's much faster than both generative approaches, such as masked autoencoders here, and also much faster than contrastive approaches, such as MDGRL. So to wrap things up, I will just mention a few different directions of research. I think there's three main parts where we can extend this work. So the first one is just theory, of course, which is very interesting, and it's understanding how learning dynamics and the geometry of representations are related. This is particularly important if one wants to understand what is different in JEPAs and generative models like autoencoders, because of course, autoencoders are very similar to manifold learning in the sense that you want to learn a latent representation that remains as faithful to the data as possible so you can reconstruct it later, right? But in JEPAs, this doesn't happen. So the idea is, how is the geometry of the data distorted in such a way that then it works better in downstream? So for what reason? Then in terms of modeling, I think learning representations in mixed geometries is also a very interesting direction. So, maybe having submanifolds of different curvature. That is because maybe hyperbolic representations work very well for node level tasks, but not so well very well for graph level tasks, but maybe they don't work well for node level tasks, and so on and so forth. And finally, for applications, I think due to the scaling potential of Graph-JEPA, I find that it could be interesting to see how it would perform in large-scale molecular learning or also large-scale shape understanding, given that these are both, usually when you go to scale, they can become computationally pretty demanding. So finally, I just need to have a huge shout out and thank my co-authors, Han Li from Michigan State, Professor Gillian Tang from Michigan State, and Professor Michael Pistani from the University of Verona. And yeah, thank you very much for your attention. I'm sorry for being a bit long with the presentation, but here are all my contacts. In case you have any questions, please send me an email. I tend to reply You can find also all other contact information on my website. And finally, you can also find me in the Geometry and Topology Slack group if you're in there. So send a message, send an email, whatever, if you have questions. And yeah, thank you again for your attention, and have a great rest of the workshop.